All right, and here we go. All right, Advent of Code, day 10. Before we get started today, I'm just gonna talk about some very, very small but important refactors that we did yesterday to part 9. Thanks to the watchful eye of Sujin from the Toronto.js Slack, who found a couple of issues. One was right here, I had done continue instead of break. And of course, continue just moves to the next iteration in this loop. Whereas what we wanted to do is we wanted to break out of the loop entirely. And so that is, of course, break, not continue. If you were watching, you'll recall that what we were doing is we were tracking the number of loops. So what we did was we would put, we initialized loops equals 0 up here. And then what we were doing is we were adding to the loops here. So break and continue appeared to be operating the same way, but of course they weren't. Continue is just incrementing the number of loops. So we're still doing the loops, just weren't counting them. So big thanks to Sujin for that. He also pointed out you'll notice that yesterday I'd started writing like a sum method, and just as like a refactor to remove the array reduce from here and just extract it into its own thing. So one of the things he also pointed out was what had tripped me up in that sum method was that we were passing the array as an argument, and then we were assuming inside the sum method that it was a series of arguments that had been exploded, and of course we weren't exploding it, and that's why it didn't work at all. So I just thought it would be nice to put this in and just have something that we can look back at in the future, because we seem to be summing arrays so often during Advent of Code that it would be nice to have this. I think right now I've broken it onto a couple lines, but I think if it's committed, I don't remember if I committed it, excuse me, but if it's committed, then it would be committed as like as maybe a one-liner like this, which is something that I'll do quite often and then have to realize that, of course, that looks terrible. And then I have to go back and split it onto several lines so you can read it. But I'm just going to leave as is for now, just so it doesn't come up as a diff during Git. But enough out of that. Let's get started on part 10. And part 10, it looks like, just from the very superficial chat that I saw in the Advent of Code channel on Toronto.js, looks like a doozy. So this is where I may begin to regret live streaming these. But of course, this is sort of what we were, what I was sort of like, I don't know, expecting, is that we're going to have some of these really challenging ones, and that it's important, I think, for people to see that they're challenging, and to see the kinds of things that we get tripped up on all the time as even more experienced developers. So let's take a look at day 10 and we'll see what we got. Day 10. All right, adapter array. Is this about Mac adapters? I'm just gonna copy that text into my buffer. Okay, patched into the aircraft's data port. Oh, here we go. You discover weather forecasts of a massive tropical storm. Before you can figure out whether it will impact your vacation plans, however, your device suddenly turns off. Its battery is dead. Okay, you'll need to plug it in. There's only one problem. The charging outlet near your seat produces the wrong number of jolts. Okay, it's a new electronics term. Always prepared. You make a list of all the joltage adapters in your bag. Each of your joltage adapters. I love who write these. Whoever writes these is great. Rated for specific output joltage. Your puzzle input. Any given adapter can take an input 1, 2, or 3 jolts lower than its rating and still produce its rated output joltage. Okay, so we have adapters. They're rated for a joltage. and any adapter can take an input of 1, 2, or 3 jolts lower and still produce its rated joltage. That's interesting. So these are like forgiving step down joltage adapters, I guess. In addition, your device has a built-in joltage adapter rated for 3 jolts higher than the highest rated adapter in your bag. If your adapter list were 3, 9, and 6, your device's built-in adapter would be rated for 12 jolts. There's a lot of stuff going on here. Okay, treat the charging outlet near your seat as having an effective joltage rating of 0. Okay, that's weird. Since you have some time to kill, you may as well test all of your adapters. Wouldn't want to get to your resort and realize you can't even charge your device. That is true. All right, if you use every adapter in your bag at once, what is the distribution of joltage differences between the charging outlet, the adapters, and your device? For example, okay, suppose that in your bag you have adapters with the following joltage ratings. Okay, 16, 10, 15, 5. With these adapters, your device's built-in joltage adapter would be rated for whatever the highest is plus 3, so 19 plus 3 is 22. Because adapters can only connect to a source 1 to 3 jolts lower than its rating. In order to use every adapter, you need to choose them like this. Okay, so we start with 0. Okay, joltage rating 1, 2, or 3. Of these, only one is an adapter rated 1 jolt, a difference of 1. Yeah, so 1's the only one within 3. So, oh, I see. You gotta, I guess you have to stuff them together so that all the numbers are within 3 of each other. From the 4 jolt rated adapter, the adapters rated 5, 6, or 7 are valid choices. However, in order to not skip any adapters, you have to pick the adapter rated 5 jolts. Oh, wow, okay. I'm starting to get the idea of why people were talking about this being, I think the one thing that I saw mentioned was like, oh, I'm just gonna let it run. And it was just like, I see, we're gonna be checking a lot of doing a lot of like conditional branching, like, oh, what if I go this way? And then, oh, what if I backtrack and go this way? Okay, so using every adapter, there are 7 differences of 1 jolt and 5 differences of 3 jolts. Here's the larger example. In this larger example, in a chain that uses all of the adapters, there are 22 differences of 1 jolt and 10 differences of 3 jolts. Okay, find a chain that uses all of your adapters to connect. That's just flexing. To connect the charging outlet to your device's built-in adapter. And count the joltage differences between the charging outlet, the adapters, and your device. What is the number of 1 jolt differences multiplied by the number of 3 jolt differences? Okay. Hot damn. Okay, that's interesting. So, I mean, this is like, I remember messing around with like Sudoku recently and just thinking that I remember doing a Sudoku puzzle when I was like 20. So like in like 1999 or 2000 or something like that. It was a long time ago, and I was doing it in PHP, and I was like, oh, I write software. I should be able to solve Sudoku in software. And I remember doing exactly what new devs I find do, which is trying to take how I would solve a Sudoku as a person and translate that into software. And I remember it being really difficult and unnatural because I wasn't taking advantage of what computers are good at, which is being extremely stupid but extremely fast. I was trying to, shave dozens of calculations by doing really complicated stuff that, of course, never worked. And then, I mean, the approach that I sort of took more recently was, I think similar to what we're gonna be doing here, which is why I'm talking about it, which is just sort of like reality branching, like going forward saying, okay, we have, 2 possible solutions. One will probably work, the other probably won't. So let's just try one and then keep going. And if that fails, we can roll back and go the other way. So sort of like trying every possible thing, but depth first. So the first time we win, we can discard the rest of the ideas. And of course, that's what computers are very good at. They're very good at doing simple operations in a lot of them. So, okay, enough talk. Let's write some code. All right, so let's paste that in. Battery's dead. Okay, so this is going to be one of our puzzle inputs. I think we got 2, and this one. So with these adapters, yeah. So the highest with this input is going to be 19, and then we got 22. And all right, this is sort of like what they told us would happen. Okay, and here is a larger example. Input. So they give us 2 inputs. Of course, I've already called this input. Larger input. Let's call this larger input. So in this larger example, okay. So let's look at the first example first, because it's smaller and probably easier to deal with. So this says that we should find 22 jolts is the jolt of the adapter, or of our device. So we have to get there, and we want to use them all. And it tells us how to use them all. And then it tells us down here there's 7 differences of 1 jolt and 5 differences of 3 jolts. Okay, so 7 times 5. Okay, so the answer that we'd be looking for is 35. That's what we'd be looking for. Okay, so let's make our usual sections. What do we have? Where we define things, we test things, and then we run the output to get the answer. So we've got our first input. Okay, we're gonna obviously need log. We're gonna need assert, and then we're gonna need to figure out how the hell we're gonna do this. Okay, so basically what we're gonna do is we're gonna do something similar to like the inputs or to Sudoku, where we have like a number of possible next steps. And maybe because it's like 1 to 3, maybe these are the ones right here that maybe these are the ones we can select from. So we got 3 choices for what the next move can be, right? So I guess what we'll want to do is we will want to say, okay, what we're going to do is we're going to evaluate the first one and then try to complete the puzzle. So that would effectively make the next thing be like that, because we've taken the 1 already. And we'll just keep evaluating until we can't evaluate anymore, until we're stuck, until we hit a dead end. And then what we'll do is we will like scratch that. What I meant to say was we're going to do number 2, and then we'll keep evaluating like this until we can't go any further, and then we'll try 3. So basically we're just gonna sort of like try everything, but we're gonna do it depth first rather than breadth first, so that as soon as we find an answer, we can just back out. So that's my thinking. So let's do that. The first thing is we've got okay, so we're gonna have to track. I mean, we could do this recursively, so we could. And I think that's sort of the approach that I took with the Sudoku, was to do it recursively and pass the next state into the next loop. And I think that makes sense because we don't want to destroy previous states. Okay, so let's figure out what we're asserting first. We're going to assert that the end array that we have. So let's see what they have. From the 1 jolt, the only choice is the 4. Okay, so we're gonna end up with 1. I'm just trying to get an idea of what we're going to be doing here. We're going to be 4, 5, 7, 6, 7. Okay, so 4, 5, 6, 7. So 4, 6, 7. So what I'm doing here is I'm trying to get an idea of what the array should look like, so we can see where what we write eventually diverges from. So 10, 12, 10, 11, 12, 15, 16. 10, 11, 12, 15, 16. 10, 11, 12, 15, 16. Getting messages. Oh, okay. 15, 16, 19. Yeah. Okay, so let's see if this is, does this cover everything in our input? Let's take a look. Okay, so I got 4, got a 5. Oh, we didn't have a 1, so we need a 1 in there. Okay. 1, 4, 5, 6, 7. Then we got 10, 11, 12, 15, 16, 19. Okay, so this is the resulting array that we're going to want to test for. So this is going to be step 1. So, and then what we're going to want to do is we're going to want to run a program that gives us this return. So we need to write a method that gives us that. So steps for or joltage adapter order for input. Yeah, steps equals the order should be that, and this should be our result for step 1. So we want to assert that order. And this is always annoying because arrays don't necessarily equal each other. So we're going to JSON dot string, or I guess we can just order dot join and put some character in here like, oops, we'll do that. Assert order is step 1, and then we'll see. Yeah, okay. So right now we need to make this order for method. So order for, and that's going to take input, and our input is going to be text. So our input, I guess what we could do is we could do basically what we did yesterday, and we could just steal this parse input, because that's, why not? We wrote it, we get to keep it. So we're going to order for parse input. So this is going to give us an input of numbers. So this is going to be adapters, an array of adapters. Okay, and we're going to have a current voltage, so current joltage, current joltage, which defaults to 0, which is the plug in the wall. So, so this adapter list is our current state of what's available, and then this is the joltage that we're after. In fact, let's start with current joltage first. So my thinking here is what we'll do is we'll find an adapter that we can use, and then we'll just try to recursively call order for. So okay, so what does that look like? For adapter in adapters. Is it adapters or adaptors? It is adapters, I think. Yeah. Adapters, yeah. Okay. When this has to be within 3 volts, does it have to be higher? Yeah, it does. Okay. Okay, where adapter is less than or equal to current voltage plus 3. Okay, so basically we're just going to go through this array and say, hey, for any option that we have that's pluggable, what we want to do is let's make a new array of adapters. So new adapters equals adapters A for A and adapters when A isn't the adapter that we want. So there's probably a smarter way of doing this. I imagine what we could probably do is, I mean, we might be able to like find the index and slice them out. I'm okay with doing this for now. Okay, so we got new adapters. And what we'll do is we'll call order for current voltage plus the adapter that we're using, comma, new adapters. And we'll return that. And if we get here and we haven't, I guess what we're gonna need to do is we're gonna need to track the fact that it won or the fact that it lost. Like we need some indication that it was able to successfully, so what is a success condition? A success condition is that we run out of adapters. So if so I guess maybe what we should do is we should also pass in the chain of adapters that we're using, because otherwise we're going to have to track at every level. We're going to have to like return the current voltage, and then we're going to have to like roll up the voltages, which might be kind of a pain. What we can also do is we can just ask the next iteration to track what the current state of our adapters is, and then we can record, or we can just pass that whole thing back. We can return the whole thing. So that's what I'm thinking is like, what is this going to be? Current adapter or plug adapter chain. These, okay, this is where the wording becomes very bad. So new adapters and then adapter chain. Well, what we're gonna want to do is we're gonna want to, push adapter and adapter chain here. Except this is gonna be, no, this is new adapter chain equals adapter chain and add. We're gonna want to just create a new copy. Okay, so new adapter chain. Okay, so here we go. We got our new adapters, we got our new adapter chain, and our new current voltage. I mean, we may as well just put it here. New voltage equals, okay. Okay. So now we're passing the new adapter chain up. So if adapters is empty, we're going to want to return the adapter chain. So that means we've exhausted all of our adapters. And then if we ever get to the end of our loop, we want to return false. So if we ever exhaust our loop. So the idea here is that we keep going in, keep going in, keep going in, keep going in, and then we have one that wins and then returns a value, which is going to be the adapter chain. And if we ever get to the end of one of these, it means that no, we've gotten stuck. We've hit a dead end. And so now we need to respond to this false. Or maybe we don't have to respond to the false. Maybe what we can do is that would just move on to the next part of the loop, which I think is what it'll do. Okay, well let's see what we get back for order 4. So order 4 parse input, adapters is empty, adapter chain is empty. Oh, current joltage is 0. That's what we need. Order for 0. Current joltage. Okay, so let's see if this runs. It doesn't run. Assert is not a function. What? Oh. Acquire. There we go. Okay, so false equals true. So we got presumably something. So let's look at it. What did we get? We got an empty array. Okay, so let's start logging what we're doing here. So, okay, log. So we got new adapters. Let's see how many loops we're even doing. New adapter chain and new joltage. We're doing no loops. Return equals, oh, because we're not returning this. Return ret if ret. So if, so this is bad. So basically we're capturing the output, and we're gonna return the output if the output is truthy, or do we always want to return the output? I think what we want to do is we always just want to return the output. Return. This is going to return from order for, rather. Yeah, so no, we just want to return if it's truthy. Okay, so let's try that. Nope, still nothing. And it's not even logging this, which is weird. Let's log like hi. Okay, so what do we get? We got one hi, we got an empty array. Okay, so for adapter and adapters, when add is less than or equal to the current joltage plus 3. So let's log something here. Let's log trying add. Probably something super basic that I've screwed up. So it's not even getting here. Did I screw something out about adapters? Let's find out. Log adapters. Okay, no. Return adapter chain if adapters is 0. So am I still logging adapters? I am not. So okay, so we're returning here. Return adapter chain. Simon operator. This is why I always like to use is because I'm an idiot and I always do the same friggin' thing, which is put a single equals. Okay, all right, so order.join is not a function, so it's not liking this on line 129. So order equals orders for. So in theory, all right, at least it's running, so that's good. It's running. It's giving us one. It's starting one loop. It's giving us this. So new adapters, new adapter chain. So new adapter chain is, this is wrong. Adapter chain. No, adapter chain is right. It's new adapters is wrong, and that's because this needs to be in parentheses, I think. Yeah, there we go. Okay. Okay, so new adapters. Let's not log that. Let's just see if this finishes. It does finish, but it gives us false. Okay, so this is just so this is going to give us the new adapters. Let's run that and see what it's doing. Oh my god, this is a lot of output. Okay, so it seems to be doing what we want it to do so far, which is it's creating a new adapters where it's pulling the 1 out of here, and then it's giving us the current joltage of 1, and it's giving us this set of visited ones. It does the same thing, 1 4 1 4 5, and it does this a while, and then we eventually get to the point where, so this is interesting. It seems to be screwing this step up, where it's like Look at this, 1, 4, 5, 10. It just added 10, which is totally not correct. So, I mean, so what's our, well, what was our last current joltage? Oh, it was 10. Oh, interesting. So maybe how we're computing the current joltage is wrong. Oh, maybe it's not. No. 10 is the correct. Oh, you know what? The current joltage is the last joltage, not the adapter plus. Okay, so new joltage equals add, I guess, is what we want. We want the joltage of the last adapter. So let's try that. Okay, and that's what it was. Okay, so what we were doing is we were taking the current joltage, and if we had a 5 joltage adapter, we were adding 5 to the current joltage, which is incorrect. What we actually just want is we want the resulting, that's what they're named for, is they're named for the joltage that they give back. Okay, cool. So that's neat. We'll just put that there, return ret if ret equals whatever. Cool, so that's our tests. Let's assert that it works. It does not. Order join is not a function. So this is, oh, this is giving us back false. Did I just screw something up here? Let's find out. No. Oops. So, oh, okay. So this actually didn't work. I just assumed it did. Let's put that assert down at the bottom. Okay. Just so we can not get confused by that. So how did this go wrong? Look at this. So this is what we have left. So return ret if ret, and so return ret, I guess, or we don't want to return. We don't want to return yet. We want to continue. We want to continue unless ret. Okay, so let's see what happened. Let's see where this went off the rails. Okay, so we go 1, 4, 5, 7. And what is the order that we want? 1, 4, 5, 6, 7. So it made a misstep here in that this is a perfectly legal move, but this is where it started to go off the rails, where and it should backtrack to this point in the future. So I guess what I'm going to do is I'm going to see if I wish I could just copy that out, but maybe I can copy it, open it in a new tab, and I want to find 1, 4, 5, 6 to see. Okay, so at some point we get here and we get stuck, and then we back out and we start going down this instead, which is good, that whole, or that path instead. So I wonder if we ever get near the end. Oh, of course these, yeah, what we want is we want to look for some combination of these in order. So I'm gonna, you know what, I'm gonna log them differently. I'll say dot join. There we go. So let's try that. Okay. So log new adapters, just so we can have some predictable output that we can search for. Okay. All right. And we are going to look for, whoops, how close did we get? We did not find any of those. Okay, so, whoops. Okay, so 11. So was it just because of that comma? Yeah, okay, look at this. So we did get here. So we got to this point where we had the correct order, and so that means that order for, so return ret if ret. So this should have returned the adapter chain. And of course, this is comparing it to an empty array, and maybe an empty array isn't in an empty array. So adapters.length. Let's see if that does the trick for us. No, it still doesn't do the trick, but it probably does. I think this gives us the right 1457. No. Well, let's take a look. And let's find that. So it doesn't log what we're looking for. 145, whoops. So I never, so that wasn't it. Okay. Whoops. Where am I? No, get out of there. There you go. So unless adapter's length. So let's say if adapter's length is 0. Turn adapter chain, and we'll log adapters log win. Okay, so do we ever find win, I guess is the question. Did we ever get here? We did. Okay, so we did get to win, and that's incorrect. This is just not correct, because 19 is not within 3 of 6. So yeah, that's super weird. How the hell did we get here? How? Okay. So something is clearly very wrong. Okay, so adapters when the adapter is less than or equal to the current voltage plus 3. So this should be an empty array if the only remaining adapter is 6. It's interesting. Just what's this? Oh, we've got Tronajess. Speaking as someone who did a ton of useless work, let me know if you'd like tips as you go. Yes, love tips. So I think have. Oh, okay. We got people actually watching on the live stream, so that would be cool. Can you use the YouTube live chat? Cool. Okay, and I see Evgeny has joined the live chat. Hey, Evgeny. Welcome to watching me get confused about joltages. Okay, so and Blake has joined. Hello, welcome. Yeah, would love tips. If you can see what I'm doing wrong, that would be great. So what I'm doing is basically I'm recursively, okay, tip 1, you can't plug a lower voltage adapter into a higher one. So is less than or equal to current voltage plus 3. Oh, so right here, oh, this is less than or equal to, okay. So current voltage is less than add, okay, so maybe that's enough. So when, and is that the right answer? I think that's the right answer. Okay, yeah. So that was beautiful. Thank you, Blake, for telling me that. Okay, I'm like less. Blake, you're a lifesaver. Gold star for you. And then, all right, that's our assertion. So where's this log? We don't need anymore. Okay, we're logging order 4, and that's the correct thing. So beautiful. Yeah, wow, good find. What does Blake say? Blake also says, also, you don't need to backtrack since there's only one valid choice at any point. So that's true. So I think what Blake is saying is he's saying that at any one point, since these go up sequentially, he's saying there's only one valid choice. And that's true. And you know what? That's especially true because it can only be a higher joltage. So super interesting. So I guess what we should do is we should just, to make this run a lot faster, we can just sort the array. So let's see how many loops we save. Lops. Loops equals 0. And every time we're in a loop right now, oh no, we'd have to pass these. Yeah, we'd have to make these loops outside this. Whoops. Whee. So let's do that. Let's loops equals loops, brother. And then we will order for, actually we'll say loops equals 0 if current joltage, or unless current joltage. So this will reset the loops every time, and then we can say loops plus equals 1, and then so if ret, turn ret, and we'll also log loops. I wonder if that'll be enough. So 22 loops. And then what if we sort adapters? Adapters dot sort. So let's try that. 11. So yeah, that cuts this in half. And that is nice because on the longer inputs, that's gonna probably pay huge dividends. Okay, so cool. Still work? It does. Okay, so let's try our longer input. Or actually, I guess we can move on to step 2, which is how many steps of 1 and how many steps of 3 that we need. Okay, so we've got our order. So we need a function that basically goes through the array and just sees what the diff is between these and then counts the diff. Okay, so we need diffs. So diffs order. We're gonna have, yeah, and then we want to count the diffs that are 1 and then count the diffs that are 3 and then multiply them together. So let's make diffs. Diffs. Okay, so we've got our array. Let's call it that. And then for, I guess what we'll do is we'll just have an empty array, ret equals that. And then for L in array, we can ret push. Well, what we could do is we could just unshift them. We could unshift the value. I guess, I mean, we could do it this way too. We could say, you know, the head value and then the rest. And what we really want to do is we want the head and the next and the rest. Next is a keyword. So 1, 2 equals array. But oh wait, that's not. This is crazy. I don't know why I'm doing all this dumb work. Okay, so we want effectively, so L. So we want array at index plus 1 if there is one. So when index is less than array dot length. So we want minus L. We'll ret push. So what are we doing here? We're creating an array, and then we're saying, hey, for every element in the array, until the last one, because we can't subtract the next element. We have no next element to subtract from. Then we're going to push this into the return array, and then we'll get the right back. So let's see if this gives us something sane. So it gave us something plus not a number. Let's just skip it. Let's do it this way. Unless, oh, you know what? And we also want to skip. We also want to skip the first one. 3 1 1 1. So that would give us 3 1 1 1 3 1 1 1 1. Oh, 3 1 1. So this last one is not being evaluated, or this last 3. Oh no, this last 3 did get evaluated. So this is all fine, but then we've got a nan, which is interesting. So why was it doing that? Array index plus 1. I guess we can just guard against this to make sure that, or is it the step? What are we doing here? Okay, so we're starting at 1 and we're subtracting the next from that. Okay, and we do that, I guess. Unless there's a value, push that. So let's see if that gives us, that just gives us, oh, we want if there's a value. Oops. Okay, so that's fine. So we can do that, cool. And so that gives us the diffs, and then what we want to do is we want something that basically does diff product. Okay, and this is going to give us an array of diffs, and that is going to, we're going to do, we want to count the number of 1s and the number of 3s. Okay, so 1s equals a for a in when a is 1. So we're going to do that length. There's probably a smarter way of doing this. 3s and then 1s times 3s. And all right, let's try that. Log. So this is giving us 24. Is that what they were saying they wanted? Let's find out. I don't think it is. In this example, there are 7 differences of 1 jolt and 5 differences of 3 jolt. Maybe what they're doing is they're counting like a 0 at the beginning because that was the input joltage. So maybe that's what we should be doing here. So let's just quickly see if that's what it is. 0, comma. No. Oh, that's diff product. We'd want to do that up here. So 28. No, that still doesn't account for the difference. Okay, so let's log the diffs. Okay, so this is a difference of 3. So I guess the first one would be a difference of 1. So how many 3s does this give us? 1, 2, 3, 4. This gives us 4 differences of 3. And they're saying it gives us 5 differences of 3 jolts. Is that... In this example, when using every adapter, there are 7. Oh, because, right. Okay, so there's the finally our device has the built-in 22 jolt adapter. So right, these are the adapters, and then there's the device. So diff product is 3 plus 1. So, and then 1s, this might be plus 1 to count for 1 plus. So this is for plug and device. Okay, so I think this is the only time we have to do that because everything else is just going to be the plugs. So this would assert that assert 35 is that, and that does assert. So I guess what we can do now is we can assert that the next test, so the next test input that we had, which was this, the larger input, 22 differences of 1 jolt and 10 differences of 3. Okay, so 22 and 10, so this should be 220. So that's the next thing we want to assert, is we want to assert and this order is actually just order 4. So that's really what we want to assert. Diffs. Parse input, larger input. And this should be 220, I think. So let's see if that works. It does. Okay, beautiful. Cool, we don't need to assert those anymore. Cool, so both our assertions pass now. And let's grab the input and see if we get the right answer. Okay, new file, input.coffee, module.exports equals, whoop. All right, beautiful. So let's do log diff product diffs order for parse input, and we'll just do require input. This is taking a while. Ooh, I can hear the fan turning on in my computer. Oof. I guess one thing we can do is we can speed this up by saying only support last current joltage. So only sort it on the way in. Oh, maybe that's what it was. Is it just a lot of sorting? How big is this input? 109. Wow. I guess it's just gonna be testing a lot of combinations. Hot damn. Yeah, this is taking a long time. I wonder if maybe there's a way we can speed this up. How could we speed this up? Well, let's take a look. So diff product, we only run this at the end. Diffs, we only run at the end. Parse input, we only run at the beginning. Okay, so one way we could speed it up is by only sorting the first run. We only care about sorting it once. And I'm just doing a length check here, that's fine. So every time we do this, we're running through the entire array of adapters, and the entire array of adapters, we're comparing them. So reasonably, we're only ever going to be checking the next 3 elements in the array. And also, yeah, this, I guess what Blake was talking about earlier was that it will only ever be able to choose the next one because the voltage has to be higher than the previous voltage. So maybe what I'm doing here just doesn't make sense at all. But I guess the the other question then is, do I have to test these at all? Or, I mean, is the answer any different from just sorting the array? Like, can the answer be any different from just sorting the array? So that's another question as well. And then, like, what's the point of this? Would just sorting the array and like testing it work? The answer might be yes. David James has joined the chat. He says, if it's working correctly, it should be efficient. Okay, so that's an interesting hint. If it's working correctly, it should be efficient. So maybe that's what he's getting at, is that if it works, then maybe it should just be sorting the array. So what was all this work for? That's the real question. So what if instead of the order for, okay, it's crazy time. What if we just did, instead of order for order for, what if we just did sort? Yeah, because fucking JavaScript sort. let's just sort the input and then see if that works. It doesn't work. Input dot sort. Oh yeah, I need to parse input. Yeah, let's do sort input. Input, I guess this is an array, and we'll say array dot sort, and then pass back array. So then this would be, sort input, parse input. And then this is larger input. Larger input. No, so that's not working either. False equals true. So it looks like, oh, is that, larger input. Okay. So order for is doing something other than sorting, it looks like. Oh, we got more chat. I can hint bigger. Yeah, you know what, do it. If you need to use all of the adapters and each one has to be bigger than the previous, yeah, so this is just a sort. But basically there's sub problems that are being solved over and over again. There's sub problems that are being solved over and over again. So I guess the question is like, let's take a look at this. Like, what if we had this array and we want this to be in the order of, so yeah, let's do this. So let's log that. And is this is no different than just the sorted array, right? So so why sort input? What is sort input, parse input, input? Let's log that. Maybe I just fucked that up. Let's take a look. So that is, oh my god, yeah. So that's why it's not working, because it's doing a natural sort, like a. These should be floats though, right? Like, okay, am I crazy? JavaScript array sort float or numbers. Why are my numbers coming back? Sorts values as strings in alphabetical and ascending order. Yeah, what the hell? That's super annoying. Come on, JavaScript. Okay, so you can just pass in a method. Okay, that's super upsetting. CoffeeScript, there we go. And then that will pass. Whoops. the result will be back. So okay, so now assert. Oh my god. Okay, so sort input, parse input. Really? Okay, so this is where we got. What is chat? There's subproblems that are being solved over and over again. So what does he mean by that? That's the question. Diffs, sort input, parse input. And this gives us 2590. So let's see if this is correct. Maybe he's giving me a hint for part 2. That's the right answer. Okay, going to part 2. So we did a lot of we did a lot of unnecessary work that will hopefully become necessary in part 2, or we just wasted a lot of time. In fact, we didn't need any of this giant thing to get the answer. So that's upsetting to me. So let's take a look at part 2, and we'll see if maybe we can feel better about ourselves after that. To completely determine whether you have enough adapters, you'll need to figure out how many different ways they can be arranged. Okay, so now I'm starting to feel a little less bad. Every arrangement needs to connect the charging outlet to your device. Previous rules about when adapters can successfully connect still apply. The first example above, the one that starts with 16, 10, 15, supports the following arrangements. Okay, so we don't have to use every adapter. And you see, look, what they're doing here is they're putting like, oh, this is the 0, and this is the 22, just to sort of like help indicate to you that these need to be accounted for when you're doing that weird add multiply thing. Okay, so the charging outlet and your device's built-in adapter are shown in parentheses. So given the adapters from the first example, the total number of arrangements that connect to the charging outlet to your device is 8. The second example above, the one that starts with 28, 33, 18, has many arrangements? Here are a few. Okay. In total, this set of adapters can connect the charging outlet to your device in 19,208 distinct arrangements. You glance back down at your bag and try to remember why you brought so many adapters. There must be more than 1 trillion valid ways to arrange them. Surely there must be an efficient way to count the arrangements. So they're giving us a pretty strong hint here that we don't want to count 1 trillion things. Oh, we got more. We got more comments. This was the part that took me forever. No pressure. Yeah, none at all. Okay, so this is a pretty strong hint that we don't want to count 1 trillion things. Surely there must be an efficient way to count the arrangements. What is the total number of distinct ways you can arrange the adapters to connect the charging outlet to your devices? All right, are these the same examples as before? 28 and 3? I think they might be. 28, 3, yeah, okay. Oh, that was the first half of the puzzle. So yeah, they use the same examples. So let's copy these into part 2, and actually let's just see day 10. Copy 1.2 coffee. Okay, we're just going to copy it over, and then we'll write over the description. All right, part 2. Okay, and right, these are plain. I put these plain things in because otherwise GitHub will try to colorize these as CoffeeScript because it's Markdown. Parser will just assume that it is CoffeeScript because it's a CoffeeScript file, even though it's just it's actually just should be evaluated as Markdown unless it's indented for spaces. Okay. So this is maybe when we're actually going to take order 4 out for a spin, but I'm not sure. So let's take a look. All right, let's take a look here. So what are we going to do? Oh, we got more comments. Start at 0 volts, then 1. So that is the question. Start at 0 volts and then 1. So these are the valid ways that we can do this. So, I mean, effectively what we're doing in our order 4 is, you know, we start here, and then we add 1, and then we kind of branch off, and if there are any other possibilities, we keep adding them. And then what we'll want to do is we want to get to 22 volts, and we want to stop if we exceed 22 volts, which is something that current order 4 doesn't do. So first of all, let's uncomment that. So when current voltage is less than the adapter, so we're gonna need to know the max adapter size. Well, I guess maybe that's no. It's always gonna be the biggest adapter. Okay. What was it saying? Then you check 1, 2, 3, n plus 1. Am I hinting too much here? No, you keep hinting. I appreciate it, David. So yeah, n plus 1, n plus 2, n plus 3. So I mean, basically, I think it's sort of what we're doing here. Except what we're doing is we're looking through the whole array for what those could be. And I guess what David's pointing out is that we don't need to look through the entire array. What we can do is we can peek at the next 3 values effectively. And maybe that'll speed things up dramatically. So let's try this. So order 4 still works for these assertions. So let's make sure that any changes that we make still work for this. So what did we just do something? Order 4 input is not defined. Parse input. Oh, right, because we don't have our inputs from previous. So let's grab these input and larger input. Whoops. There you go. Whoops. Come on. There we go. Input, larger input. And we'll go into here and we will grab our inputs. Okay. Okay, so these are still working. So let's make sure that any changes we make to order 4 still works. So instead of that, so really what we want to do is we want to grab the first 3 adapters. We really only ever care about add an adapters 0 to and including the 3rd one. So maybe that's enough to speed it up. No, that breaks. So you get a path from some arbitrary n to max, but once you've figured out from n, you never need to compute that again. Yeah, so that's sort of, I think, how this works already because it's recursive. So what it does is it computes the current state, and then it tries to find the next state by calling itself again with sort of like the next stage. So, I mean, what we could do is we could try this and see if it's fast enough as is. And maybe it will be. Not sure. And what is David saying? He said, oh, that was the same thing again. Oh, there was no new comment. I'm not sure. I'm getting these like these weird Slack comment clicky sounds, and I'm not sure if they might actually just be coming from Slack because I have Slack open. Okay, so I guess we can try this. Let's do that. Let's see. What we want to do is we want to count the number of successful things here. So adapters.length, this win condition is no longer true. What we want to do is we want to see if, so we're going to need to know the max joltage going in. So it's going to be similar to this method, but it's not going to be this method. So let's do here. So what is these are orders for, and we're going to want a target joltage equals, I guess we don't want equals anything. We want a target joltage. And we're going to need to determine what the target joltage is. So target joltage equals, and it's always 3 higher than the highest one in the array. So this is going to be adapters. Okay, adapters is going to be these. So adapters. Oh, this adapter sort is wrong too. This should be what do we have? Sort input. I guess we're always sorting the input on the way in. Maybe. Let's do sort input. There you go. So we don't need to sort the input, and that was wrong anyway. So that was sorting. God, that's so annoying. JavaScript, why are you like this? Okay, does this still work? Yeah, it does. So, and we want to get rid of that as well. Okay, so target joltage is going to be, so let's assume it as sorted. We're going to do adapters. Actually, we can just get, we don't care, and last equals adapters, and then we'll just return last. Maybe what we should do, we should put the sort input. Okay, so target joltage. So orders for target joltage, and then when we call this again, we'll want target joltage. Okay, so what are we doing? We have orders for, and we'll return adapter chain if current joltage is so +3 is greater than or equal to target joltage. I guess we can say if target joltage is greater than or equal to current joltage +3, or less than or equal to. And so if we get an adapter chain, so this means we're going to be collecting winning scenarios. We're going to be collecting arrays of correct chains on the way down. So I guess what we'll do is every time we call orders for, what we'll want to do, or I guess every time we split, we're going to want to, yeah, we're going to want to like what are we going to call these? Like successful orders? I don't know. Rets for return values. Okay. And then here, what we can do is we can rets.push ret if ret. So this is kind of terrible. And then then we'll return rets. And then I guess what we'll do is we will just, so this is going to be, it's going to be a big set of empty arrays. Because we're going to want to flatten it. So let's grab flatten and unique, or just flatten, I guess. Flatten from underscore acquire underscore, and then we're going to want to return flatten ret if ret. Nope, not there. Return flatten rets. So we're going to return these all the way down. I'm going to get rid of that so I don't automatically try to do that or edit that in the future. So I guess what we're going to want to do is we're going to want to start logging like the simple case. And let's see, and it's orders for, and we want to do target joltage adapters. Okay. Okay, and then we're going to want target voltage adapters. Where is 4? And then the current voltage, and then the adapters is our input. So let's see what we get back here. Something broke. Order for is not defined. Order for is not defined. Order for. Order is 4. Whoops. Try that. Okay, so this is giving us 1. That's currently not the correct thing. Ooh, David's dropping one last thing on us. I didn't sort and never kept the path array at any point, not for part 1 or part 2. Okay, interesting. So he's saying that he chose a different way to do this, which may be the correct way, like the correct way, rather than a correct way. And he's saying he never sorted, and he never kept the path array at any point. So that's interesting. So basically what he's saying is he's strongly hinting at the fact that there is certainly another way to do this, and this may not be it. So that's good to know. So thanks. Yeah. Okay, another thing, adapter chain. So adapter chain. So I'm gonna continue looking at this solution because this is the one that I've got in my head, but it's good to know that maybe there's another way that we should be thinking about doing this. So this is pushing through an adapter chain all the way through, and we return the adapter chain if we're within striking distance of our device. And then basically what we're doing is we're going to add that to our return values. And then this should theoretically just get fed back up the chain, but for some reason we're just getting a 1, which is weird. So this adapter chain, okay, if target voltage is less than or equal to, what is our target voltage? I guess we should find that out too. So what's target voltage of adapters? Log, oops. So 4, so that's wrong. So that's pretty clear. So our sort input adapters, sort input, where's sort input? This should be B minus A maybe. Yeah, okay, cool, and that gives us an answer. So it's amazing that sort input even worked on the other one because we had it backwards. So B minus A. Does this still work? This no longer works. Let's try A minus B. Okay, I'm very confused. So sort input. Let's double check sort input and make sure that it's actually. Let's log adapters. Okay. So adapters. No, this is now going backwards, but it's giving us It's giving us, okay, I'm very confused now. So this should be A minus B, and that should give us the correct order, but it's giving us the wrong, oh man, okay, that's why. There we go, okay. So this gives us the right target joltage. Okay, should always test every little thing as we go. We should always test that. Okay, so this is, oh, so it's just flattening the whole thing, right? So we don't want to, we only want to flatten the return values, right? Because the return values themselves are arrays. So let's see what we got. We got array, array, array. So there's three, there's three possibilities. Is that even right? That's probably not right. No, it's like, okay. Here, let's return. So if we're on the outermost one, if our current joltage is 0, unless current joltage, return rets, else let's return flatten rets. No, this is still doing the wrong thing. Flatten rets. Do I just have this backwards, or am I? No, I'm a crazy person. No matter what I'm doing, I guess I never want to flatten the arrays. I guess I also don't really care. I don't really care if they continue to be arrays at this point. So let's do join. Okay, and then we can just return flatten rets. Nope. Oh, right, because these are going to get flattened upstream and then they're going to get turned into, yeah. All right. So definitely going down the wrong path here, where however I'm returning this is not great. So let's not flatten these and see what our input looks like. So this is still, so rets is an array, and we're pushing a string onto the array. Am I flattening? I'm not flattening this anywhere. So I guess the question is, why am I getting one long string back? I feel like my instinct is telling me that I should have an array of strings, like this should be the first string, and then this should be the second string, and then this should be the third string, and so on. Let's also quickly just take a look at these and see if these are even remotely close to the right answer. So let's find all the ones. Okay. So are these even remotely close to the right answer? That's the question. So they all end in 16, and this first one should end in 19. So, I mean, they're not correct unless I'm just not recording the 19, because these all end in 19. So that could be one hint of the problem. So return adapter chain. I guess we should, yeah, we're doing this check. We're doing this check in the wrong place. What we should be doing is we should be returning that maybe down here. We should be adding that down here. Yeah. All right. I'm gonna take a quick bathroom break. I'll be right back, and then we'll do more. Oh yeah, all good. Okay, back to it. All right, where were we? So we determined that we were returning in the wrong place here. So this needs to go somewhere else. Basically what we want to do is we want to push, right, okay, so if we're within range of our target joltage inside this loop, then what we want to do, so if target joltage is less than add plus 3, less than or equal to add plus 3, what we want to do is we want to push, so rets dot push, what is our adapter chain? So yeah, new adapter chain. So let's just do that. Let's let that do the work, and we'll say reds push new adapter chain, and then continue on to the next one. And otherwise, then we'll just keep going and return ret if ret. Does that make sense? I wonder if that makes sense. I guess we'll find out. So this at least is giving us it's giving us one answer, which isn't great. But it's giving us an answer, which is nice. So what do we have? Okay, so basically what we're saying is if the target joltage is less than or equal to add plus 3, then we push this new adapter chain, and then we want to return. All right, so this is only going to give us otherwise return ret if rets. So basically this should be returning rets all the way down, but are we only returning, like, what are we doing with these? This is where it gets confusing, is like this is where recursive programming gets confusing as well, because you have to remember, like, oh, where are we, at what level are we, and what do we know here, and then what are we doing with the response? So if we get a return, so before what we were doing is we were just kind of trying to like do a flat return out, like we're just saying, hey, if you return all the way up the chain, and because it was the first one that we were looking for, but now we're trying to collect them. Otherwise, I think what we want to do is we are going to be getting an array back, and if we are getting an array back, then we want to, but we don't want to return here. What we want to do is we want to push these onto rets, I think. Oops. So before, what we're doing is we're just returning, but I think what we actually want to do is, you know, if we get a return value here, what we want to do is we want to push it onto the return values that we care about. We want to add it to our collection. And then eventually we'll just return rets from this outer loop down here. And that gives us, I mean, this is giving us some arrays. I don't, yeah, that's weird. New adapter chain. Let's do this thing with the strings again, where we join with the strings, and see why can't we? And then maybe we can flatten it. Okay, so this is still, so it's giving us answers, which is nice, but it's still giving us these answers that end in 16, which is weird because at this point, if target voltage is less than or equal to add +3, so this new adapter chain should include that last 19. So our target voltage in this case, what did we decide it was? Was it 9? Oh, maybe it shouldn't be 19. Maybe it should be 22. Oh, it should be target voltage +3. Right. So our target voltage is wrong. Our target voltage should be +3 because that's the one that we're trying to get to. Okay, so now we're getting output that looks more reasonable, more like what we want. And how many did we get here? 1, 2, 3, 4, 5, 6, 7, 8. How many did we get here? Here we go. 1, 2, 3, 4, 5, 6, 7, 8. So we got 8. And are they the same ones? Yeah, let's see. The last one, 1, 4, 7, 10, 12, 15, 16, 19. Okay. And the first one is, I think, everything. And that looks a bit, yeah, this looks about right. I'm not going to compare every single one of them, but the lengths look correct. What I can do is I can pull these in just to a text file, and I can see, just remove the spaces and then see if they match up. And that's what I'm going to do. And I'm going to remove these guys. And where were we here? Just run it. Let's remove these. Let's get rid of these. I guess what I can do now is I can just sort these lines and see if we have 2 of each one. Sort lines. Okay. So good, 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 good. Okay, so these are identical. This is identical to what we want. So we've got, so we don't use that. We use this order for. So here we are. We have some possibly confusing code that is currently working-ish. So let's see if it passes assertions. The charging outlet, okay, where is this? In total, this set of adapters can charge your device in this many ways. So 8 and 19. So there must be more than 1 trillion valid ways to arrange them. So maybe returning the actual arrays themselves is a bad idea. Maybe what we should be doing is we should just be incrementing a counter. So yeah, because the return values is really we're just counting it. It's just a value that we're passing back at this point. So let's say valid equals 0, and let's say valid plus equals to 1 instead of rets push, and then if ret equals and then we'll say valid plus equals to 1, and then we can return valid. So let's see what this gives us. This should give us, this is giving us 1. Let's push rat. So what were we doing if we were flattening the rat? So we'd want to so what we were doing is we were collecting, yeah, so we're gonna want to add whatever rex is. So this ret here is actually going to be num valid, because that's what we're returning here, is return valid. And then we're going to say plus equals num valid. That should give us 8. Okay, cool. So we're going to want to assert that assert 8 is sort input, parse input, and we're going to want orders for target joltage. Right, it's gonna be this, except adapters. So got adapters, and we're going to want to assert 8 is, and this is orders for. So it's not orders for anymore, it's num valid combos. Okay. Okay, so we've got assert 8 is num valid combos for these adapters. And let's, I guess the other thing we could do is, I mean, this target joltage, what we could do is we could calculate it here. We could say target joltage or equals to, because passing it in is really annoying. And this can be get target jolt or find target joltage, or yeah, let's do that. Find target. Let's find target voltage for adapters. So if we don't pass in the target joltage, then we will, all right, so which would mean that this would become something that we'd want to put on later. So target joltage. And then when we call this again, we're going to want to call this with target joltage last. So this will just find the target joltage for the adapters if we don't have a target joltage already, because it'll start off as null and it'll always be a number. So that means we don't need to pass this in anymore. So this gives us our initial joltage, target joltage. Okay, this is just twice. So let's see if this is blowing up yet. It's not blowing up, so that means we're doing it right. Okay, so that means that we're only using adapters once now. So this can just be that and that. So log number valid assert 8 is okay, and then here we get to assert. What were they saying on the other one? 19208. Assert 19208 is larger input. Okay, so let's try that. And that ran. Okay, so now what we want to do is we want to, God, that finished in half a second for not a huge input. So I think this is going to be slow. Let's find out just how slow it is. Okay. Oh, that's wrong, the wrong thing. Yeah, we want num valid combo. Yeah, here. Let's log. and we're going to do require input. Okay, here we go. So let's see if this finishes in any reasonable amount of time. Does not seem to be doing so far. I can hear the fan in my computer ramping up a bit. So let's think about if we can make this faster. And I wonder if this just takes a while, or if this is just something that should be fast but isn't. So what do we have here? We've got valid. So this is local valid. We add to it, and at the end we add it to our local valid, and then we return valid. This last return, I mean, we can not explicitly return it, but that's not going to do anything performance wise. So we are looping over the entire array, and that's probably pretty big. How big is the input? It's 100. So, but we're looping over the entire array like 100 factorial. So maybe what we want to do is we do want to only consider the first 3, because that would, so add for add in, so adapters, what we want to do is we want to just check the first 3 up to 3, and let's see if, so first let's turn that off. Let's see if this still passes assertions. It does not. And adapters up to and including the 3rd one? No. So I guess the question is here, what are adapters 0 to 3? Log that. 1, 4, 5, 4, 5, 6, 5, 6, 7. Yeah, I don't see why this shouldn't work. And then new adapters is A for A adapters when A isn't add. Okay, so this can actually be sped up as well, but let's one thing at a time. So assertion error, false equals true. So let's see what we are getting back. Oops. Log. Is it always giving us 1? Is that what it's giving us at the end? It's not giving us anything? Let's remove these asserts. It's giving us 7. Interesting. Yeah, okay. So why? Yeah, let's try 4 and see if that also gives us. Oh, see, so that's interesting. Well, I mean, that's going to be enough of a speed up if we only check the next 4. So let's try that. And then the next thing that we can, so let's assert these. Nope. False equals true. So what was it? Was it this one? Yeah. Yeah, interesting. Okay, so why is that? So this isn't working still. Log. Let's take a look. 527, and we're expecting something much larger. So that's adapters 0 to 5. Like this should be slicing them. 8. Is this not sorted? Are these adapters not sorted? No, sort input. So, because they also always have to be within 3 volts of each other. And if the input is sorted, I don't understand how these could not be sorted.
Yeah, how could these not be sorted? That's the real question. And why are these always starting with 1? Log adapters and then new adapters for A when A isn't. So this is a good question. Wonder, still no activity in the chat. No hints. No hints, anyone? Does anyone see what I'm not seeing? I'm not too proud to ask for help. There's definitely something that I am missing here. So what I'm expecting is, I'm expecting adapters at this point to be the next adapters, like 4, 5, 6, or whatever. And, or, 7, 10, whatever. And my logic or my thinking is that because I'm only interested in things that are within the current joltage, or within a current joltage of 3, that at most I'll only ever need the next 3 elements of the array to consider. And then that is why I'm only bothering to loop this many times. I guess what I could do, but that seems to break, and I have no idea. When I log the first 3 adapters, I'm getting some what look to me as wacky results, and that's super confusing. And this seems to kind of work on this one, but it doesn't work on the second test. So confused about that. I guess what we can do is we can just start logging stuff, and let's log adapters. And then what we could do is we could continue, or I guess we could break if add. So I mean, we shouldn't even be in here. So that's yeah. So add should be greater than the current joltage, and in theory should always be the case because they're sorted. And add should be less than the current joltage plus 3. So let's see what we're getting here. So these are the adapters. So I've effectively pulled one off, pulled another one off, pulled another one off, pulled another one off, pulled another. So we just keep pulling them off, and then we back out and we go a different route. We start pulling these off. This all looks correct to me, and they're all in order. Which is normal. I mean, this just looks normal, but I don't know why it doesn't. Are we doing the same thing? In parse input, larger input. So if we do this, this is going to give us a lot more output. So 1, 2, so this is just pulling 1 off, pulling 2 off, pulling 3 off, pulling 4 off, 7, 8, 9, 10. So this is doing the right things. So I guess I don't understand why this also doesn't work when I only loop over 3. I guess what I can do is I can say for adapter and index, and I can break if index is over 4. So that will break us out of the loop and move on with our lives. So we can try that. That gives us 1889, and what are we? This is the wrong answer, right? So that's the other thing, is it's not it's not giving us the correct answer if we do that. which is super weird because we shouldn't ever have more than 3 values to consider. Unless this logic doesn't make any sense. But so this is the other thing, is this code was working, is working to produce the correct answer, sort of. So it is producing the correct answer for the test cases. It's just taking too long, and this is what we're trying to optimize. So this is giving us 1889, and the other thing is, if we change this number, it gets closer to the correct value, which is 19208 or whatever. In adapters, when current voltage is less than all right, let's revisit some of these hints that we got earlier. So was it David was saying, so you get a path from some arbitrary n to max, but once you've figured that out from n, you never need to compute that again. One last thing, I didn't sort and never kept the path array at any point, not for part 1 or part 2. So I think he's suggesting just doing something radically different. But I feel like this should work. And I don't understand why this is failing. So I think what I'd like to do is I'd like to understand why this is failing. So we have these adapters that we have to choose from. And they should be sorted. I feel like they are sorted when the current voltage is less than add. So let's log. Let's see if we can just like log these and see if anything looks weird. So this definitely looks weird that we're considering these so many times, even though and what's current voltage, I guess, is what we want to know. What's current voltage here? So the current voltage. So why are these current voltages never less than these? So what is going on? Are we passing in? We're not passing in new adapters. We are passing in new adapters. A for A new when A isn't add. Oh, so maybe what we want to do is, since we should be guaranteeing that they're in order, when A is greater than add. So let's try that. So that should be, there we go. That's giving us the right answer. And this, okay, so I see what we're doing. So we should be, I think, discounting any solution where there are adapters that are lower than. Okay, so new adapters. Okay, so I guess the first thing we should do, at this point, we're always passing in. We're always going to be passing in adapters that are bigger than our current joltage. If any adapters are smaller than our current joltage, we don't care about them. Right, okay, so this should be much faster. And so this is giving us the right number here. So these are giving us these assertions. I don't know if this is going to be any faster here, but we can give it a try and see what it comes back with. So curiosity, is this going to kill my CPU? Let's see. CPU load. No. Okay, so this is still taking a very long time. So I feel like this may have helped a little, but it's not doing enough. And break if index is 8. We don't need that break anymore. Okay, so clearly it's just not doing enough. Okay, I guess it's just, what is it, not using CPU? I don't understand what's going on here. Is this broken? Maybe Advent of Code is just an elaborate ad for the new M1 Max. That's another possibility. Yeah, I'm expecting to see these numbers change, and they're not. I'm expecting this to report anything at all, and it's not. So what the hell? Is this just broken? It's not reporting any CPU percentage. Is it so busy that it can't measure anything internally? That's not good. What if what if we run top? Okay. So OBS is taking a lot of. I seem to have a bunch of node things running, which doesn't seem right to me, unless. Kill all node. Okay. There we go. CPU monitor is working again. Okay. Well, let's try running this again and see what CPU monitor does. Okay, so node is using 100% CPU. I guess what I could do is I could log the length of adapters to see how far through this set I'm getting. Because in theory, I mean, this would, they did say there would be over 1 trillion of them. Okay, so I feel like this solution will probably work. It may just take a while to run, but a while could be years. So this clearly isn't a good solution no matter what we're doing. What happens if I cancel this? Does node keep running? Okay, it died. It was just my computer being my computer. So we're gonna have to come up with a different solution if we want to actually get to something in a reasonable amount of time. Just out of curiosity, I'm going to log adapters.length and see. Okay. All right. So adapters.length, come on, go to the bottom. Oh wow, it's really Okay, come on, quit. Okay, this might be a while. I just want to see how far into the thing we're getting, and adapter's length. I guess what it is it's adapter chain that we care about. I wonder if we care about adapter chain. I mean, adapter chain is something that we only cared to track because we wanted to know what the chain was. So let's remove adapter chain, and let's see if that speeds things up dramatically. Ooh, stop. Come on, no, my computer. It's like, ouch, my computer. Okay, so first of all, let's assert that, okay, it's still working. We're just doing less. And new adapters. Okay. And new joltage. So new joltage, we don't even need to track that. Still works, okay. It's finishing faster too, which is nice. I can give it a try and see if that makes a difference. Probably won't make a huge difference, but I mean, why bother passing something through and maintaining all these arrays? It'll probably be a lot nicer on my memory. Monitor. Let's see, so this is node. How much memory are we taking? Memory. Java. Hello, Java. What are you doing? I don't know where node is. It's probably pretty low, actually. I don't know. Numbers is taking a lot of memory. Okay, still clearly not great. So what is slow? This could be the slow thing. This could be a very slow thing right here, where we're creating a new array of adapters. And we're only evaluating 3 of them. So what we can do is we can actually just slice it. We can say index, so this would be 0. So new adapters equals adapters index plus 1 ... Let's see if that still works. Oh, we should turn off this run thing. So that will still work. So because the adapters always need to be larger, so that still passes. And because we don't need that, and that still works. What else can we do to speed this up? So this is slicing them, target joltage. Target joltage is something that we pass in. Current jolters, adapters. So, I mean, we're still creating a new adapters array every time, which is this, which is a slice, basically, like we're slicing the array. And if valid equals, so if target joltage, then that's valid, and we continue. Else we are doing this, and then we're turning the value. So I wonder if, so either this is just conceptually the wrong way to go about this, which is certainly possible, or this is just a really bad way to go about it, which is calling a function 100 factorial times. I wonder how big 100 factorial is. Factorial. Very big. And I don't know if is that the right way to go about doing this? Is 100 factorial. So the first thing would try 3. Each one of those would try 3. So it would be like 100, or it'd be 3 to the power of 100 maybe. 3 to the power of 100. Is that correct, or is it 100 to the power of 3? Either way, it's a very big number. And only to see if, and this is only to check to see if there's a path to get from one to the rest. So what else could we do? So, and David James was saying that he didn't sort. He didn't sort, and he didn't, what did he say? He didn't sort, and he never kept the path array at any point. So what would he have been doing? So what we want to do is we want to line these up, and they have to be in sorted order, because that's how the voltages work. You have to put one within 3 of another one. And they have to add up to within 3 of your target voltage or your target joltage. Yeah, it's not coming to me the better way of doing this. But there must be a better way of doing it, or at least a better way, or a way to do less work. We could work backwards, but I feel like that's the same problem. We're just moving from a higher number to a low number approaching 0. So add index, we don't need the index anymore. Oh, we do need the index. In the next 3, when current joltage is less than that, I don't know if we need to do this check anymore. No. When add is less than or equal to current joltage plus 3. And if add, I guess just to do it the same way we did, is less than or equal to target joltage plus 3, then it's valid. No. There we go. So if add is greater than or equal to, add is greater than or equal to target joltage, oops, plus 3. That's, no, greater than, less than, equal. No, okay, let's just leave it the way it was. Okay, so target joltage is less than or equal to add plus 3, and that's valid. Okay. And if valid. So do we need to do this if num valid equals? We could just do, yeah, we don't need to even do the if. And then so this array slice here is probably these array slices are probably the expensive part, or maybe there is no exceptionally expensive part, and it's just that there's a lot of combinations. So yeah, if we look at our input, it's like, okay, so we're going to be checking. So let's start with the first line. Then we're going to be branching out up to 3 times from that, and each one of those we're going to be branching up to 3 times from those. And I guess we're going to be repeating a lot of work, right? Because if no matter how we arrive at 37, we're going to be looking at the next 3 there to see if they're valid. But wait, no, that's not good. Yeah, that's true. Yeah, that's true, because it's not, we don't care about the filter chain so much, or the adapter chain so much, as we care about the last element in the adapter chain. So really, we just care that we've explored the path. We don't care what the path is, and that's why we removed that. So what we could do is we could maybe try to cache the value for each one, so we're not needlessly computing it again. So num valid combos. So this is the adapter that we're currently on, and these are always going to be the same. So I guess what we'll do is let's make an identity map or a cache. Cache or equals. Cool. In fact, let's cache equals that. Okay, so we've got this cache, and then we'll pass in cache, and so we will say plus equals cache for add or equals. Let's see if that still works. So it finished. It was that was slower in these cases than it should have been, but it might be much faster now, and it is. Oh wow, holy shit. Okay. Okay, much faster. Let's see if this works. Answer, submit. That's the right answer. Holy shit. There we go. Okay, so that was the secret here, was using a cache. And the reason was because every time we evaluated one, we were always going to be, we were guaranteed to have the rest of the array be the same. So we don't actually have to compute this in 2 different branches, because it's going to be computing the same thing. We can compute it once and then use the cache. So that was that. Let's diff product. I don't think we care about these anymore. They don't need to be here. So in part 2, okay, so I guess what we can do is let's take a look at refactoring this a bit. So we've got parse input, that's fine. Sort input. See, this pissed me off about JavaScript. is that it tries to sort numbers as a string. Thanks, JavaScript. Find target joltage. I mean, we could just sort input adapters, and we could grab like whoops, adapters dot length of that 3 plus, and that's the target. That didn't work. Adapters dot sort input adapters. Actually, do we even need to sort the input? Adapters dot length. Well, that's not happy. So what do we do here? We're doing that. Sort input adapters. That works. So sort input adapters. So we're just destructuring it into a bunch and then the last value, and we're giving it the last value. So why would the last value of adapters be? So that's a good question. So sort input adapters will equals adapters dot length. So we theoretically want lol, but last is different. So let's log lol last undefined undefined. Oh. So -1. There you go. So we could do this. We could do 3 plus. This would be presumably faster because we're not destructuring, but I don't like it. We could also do just get the highest math.max. I don't know why we didn't do this earlier. Adapters, and we get 3 plus. Yeah, that's much better. Okay, so the target joltage is 3 plus the max. I don't know what I was thinking earlier with the sort. Okay, cool. So we've got valid equals 0. I mean, we could pass just valid in here, the number valid equals 0, and then we don't need to reset at every loop. Still works. Yeah, target joltage. So we or equals find the target joltage of the adapters, which is fine because you only need to find it once. And for adapter index in adapters for the next 3 only. I wonder if we even care about the next 3 now that we're probably doesn't even matter. We spent all that time and it doesn't even matter. Okay, for adapter index, do we still care about the index? Yeah, we do because we're slicing. So, and we're actually doing that quite a lot, I think. Oh, we're not actually because we're getting the cache back, but that's fine. So if valid plus equals 1 if that's correct, or the cache of itself if it's not correct. So we could probably refactor this a little bit, and then anytime there's like a continue, that's always like an indication to me that maybe we want to like think about how we're doing this a bit better. So yeah, so we could just say valid plus equals to 1 if that, and then continue. So else, yeah, I don't know. I'm kind of thinking Ruby-ish right now. That's my problem, is I'm like thinking about this like a Ruby thing where I can just, you know, assign it to the output of a block. I guess continue is fine. Or valid plus equals the cache for this adapter. Or we need to assign the cache and run the thing. And this will cache forward, but it's not a global cache. Like it will cache, it will be able to pass its cache down to its children. So it's still going to be doing more work than it needs to do, but not a ton, and we don't have to worry about resetting the cache. Or maybe it would be, no, it would be shared because we're passing it by reference, so it would be shared, and it only gets reset if we don't specify it on the way in, which is perfect. Yeah, okay, and return valid. We actually don't need to return valid if valid is the last thing that we've returned, but like we could just have valid like that, and that works. I like, in these cases, I like the explicit return because we're saying, hey, we're returning this value, and we actually really like explicitly are doing this. I guess also it's the last expression. I think it just reads nicer to have return valid there. Okay, so that works. We've got our assertions. We're logging our output. Let's take a look at the first one. Order for. See, we didn't end up even using this. We used something similar to it in the second one. So account for the plug and the device. Don't care about those anymore. This still works. In fact, this is slower. It's the same speed as 2. It's slower than 2. But okay, that was fun. That was yeah, that was a bit of a wild ride. I'm okay with how this turned out. Caching, again, I should have seen that coming because like every year Advent of Code does this where Flatten, are we using Flatten anymore? We're not using Flatten anymore. Every year Advent of Code does this thing where they give you a problem that basically would take years to compute, and then you're like, oh, if I just cache it, then it will take milliseconds. So it's a good lesson going forward is think about caching. Thanks to everyone who has been watching me fumble along this whole time. Appreciate it. I super appreciate the help. Love the hints along the way. That's great. It's another thing, like one of the ideas behind this is to show you that even people who are experienced writing software, we Google stuff all the time, and asking for help. We ask for help all the time. Like Evgeny, who I've worked with previously, he was watching the stream earlier. I'm not sure if he's still here. He was a great resource because he was someone I could talk to all the time in the office. Just be like, hey, Evgeny, what do you think about this? Or why isn't this working? And he was a super, super great person to bounce ideas off of because really sharp, really on the ball, and always had great advice. And that never goes away. The more you write software, the more people you talk to, and the more you ask for help, and the more you Google. And that's what's great about communities like Toronto.js as well, is that it's just this huge resource of people who can give you insight into stuff that you're not clear on or stuff that's giving you problems. So yeah, totally normal. I guess what we should do is we should commit this, and I should probably reboot my computer at some point because I have a feeling it's in a weird state. Cool. All right, that's day 10 in the can, and off it goes. And try to see if we can make day 11 happen in a little bit less time, because how long has it been now? It's been like, wow, it's been almost 2 hours that we've been going. Almost 3 hours. Holy shit, it's been 2.5 hours that we've been going now. So great fun. Thanks everyone who has stuck around, and we'll see you guys tomorrow.